Welcome to a wonderful seminar that we're going to have today. I invited a very special guest who is known not just in his own country, but all over the world. And today we'll have a seminar based on the mathematics and the history of mathematics, led by Professor Michael Lambrou. He is a well-known scholar in Greece, but also in Europe, in the United States. And for 19 years, he contributed a lot to the Math Kangaroo internationally, submitting many questions, participating in meetings. So he is the author of 800 original kangaroo questions. 240 of them were selected to be official Math Kangaroo competition questions, plus additional 100 chosen as alternate problems. He's a very respected scholar, very engaging speaker, and I'm very honored to have him here today. And before I give him the stage, I also want to thank all of you for coming tonight or today, wherever you are in the world. The seminar became very popular and known to others to sign up. We had over 400 educators that sign up for the seminar. Some will watch tonight. Some of them will watch a recording from 30 different countries. So that's the international community. That's what Kangaroo represents. And that's who we are and how we want to contribute not just to growth of one country in mathematics, but to the mathematics all over the world. And who is better than Michael Lambrou to tell us about mathematics, about connections, how mathematics can be seen through the eyes of history and anything that we do in life. So Michael, thank you so much for coming here tonight. I know it's 11 p.m. where you are, but we are very grateful that you could come and give us this lecture. So please start.
Thank you for the invitation, Joanna. I'm really glad. And also I meet nice friends from distance. I recognize many of you from previous meetings of Kangaroo, and I'm so happy to see you. Anyway, let me start. The title of my talk is How to Make Mathematics Attractive, but I will make many digressions into history, going back to ancient Greece, really, because that's a lot of mathematics come from the idea of mathematics is central in ancient Greek culture. So let me, just a minute, show you where Greece is the southeastern edge of Europe in the Mediterranean. It has a 4,000-year history. The Greek language, for example, is the same as in antiquity. It has evolved, but 80-90% of the language we speak today is identical to the language that Homer and Socrates spoke. And this is our national symbol, the Acropolis. It was a turning point in history of art and also for democracy. The ancient Athenians invented democracy and they used it in their life. Greece is famous for several contributions, at least in Western culture. In Western culture, they inherited Greek art. Here's a few examples. Theater, philosophy, and mathematics. All were high quality in ancient Greece, and they were surpassed it took more than 1,500 years before the West contributes better, let's say, mathematics and so on, that the Greeks did not know. And to show you a little bit about the influence in culture, I have a list here of very common English words and also in many European languages that are of Greek origin. I highlighted the word mathematics and problem because we'll talk about it, but let's see a little bit about these words. Music, harmony, theater, orchestra, poetry, etc. Everything that has to do around theater. Democracy, tyranny, politics, demagogue, also school, academy, gymnasium, lyceum, they're all Greek words. Philosophy, logic, physics, mathematics, geometry, etc., disciplines. In mathematics, enormous amount of words. Here is only a small list. These are the words that came into my mind as I was writing. Theorem, axiom, lemma, problem, center, triangle, parallel, trapezium, etc. Greek words, abstract words like aesthetics, criticism, phenomenon, pathos, euphoria. Words around sports like athletics, marathon, decathlon. And in medicine, anemia, anesthesia, hepatitis, anatomy, pediatrician, gynecologist, etc. All are Greek words in Western culture. And they all have, I will explain the word mathematics, which is central to my talk here, because have you realized what does mathematics mean? We know what it is, but what does it mean as a word? And the word problem, where does it come from? Anyway, the topics I will cover is what is mathematics. We all know, of course, what is mathematics, but I want to show you what the ancient Greeks knew. So I'll do historical digressions, and from there we will see some pedagogical issues that they were addressing and how they taught mathematics. And so second topic is how should we teach mathematics, and how should we teach it more effectively? Because we all know that mathematics is not a topic which is enjoyed by all students, but we have to address and see what we should do. What I'm going to say is only a small drop. There's a nice saying. It says you cannot change the color of the sea with one drop of paint. Of course, and I will not change the color of the sea. But I think I'll give some insight or summarize things we know, look at them from a better perspective. And of course, the topic is mathematics, which everybody agrees that it should be a common curriculum to all educational systems. We have a lot of variety in educational systems from country to country or from time to time, depending 100 years ago to 100 years ago. But something common to all of them is that mathematics is a main subject. And we will see how and why it started being a main subject and what are the benefits of learning mathematics, why educationalists insist to have mathematics as a main topic. First of all, let me say that in ancient Greece, they thought mathematics as culturally important. There is a nice anecdote that shows this. The source that tells us the story is in Latin. That's why you see Latin on the left over there. And the story says that one philosopher, Aristippus, he was a philosopher in Plato's school, Socrates and Plato's school. So Aristippus, philosopher Socraticus, once he was in a shipwreck. The ship he was traveling sank, and he and his friend managed to come out on land, on soil. It was an island, but they thought there were savages over there, and as they were scared because their life was in danger and they were discussing what are they going to do, how will they save themselves, suddenly they saw geometrical figures. You can see here at the bottom, they saw geometrical figures on the sand, and as soon as they saw geometrical figures, they said, these are not savages. On the contrary, if they do geometry, they have a high civilization. So, and this remained in all throughout Greek culture. It was a view, a criterion of a place with high culture. The Greeks did not invent mathematics. There is a lot of mathematics before the Greeks, at least 1,000 years before, in ancient Egypt, in Babylonia, in India, in China. But with Greeks, mathematics took another turn. It became axiomatic. The mathematics that we know and we follow today, you have to support every step, and it is a mental exercise. In fact, it started with philosophers. This painting is in the Vatican, is a School of Athens of outstanding Italian Renaissance painter Raphael. It shows a lot of philosophers and scientists, ancient, mostly Greek, but there are also Arab scholars and so on, but they're mostly Greek. They did not live at the same time. From some of them are the elder ones to the younger ones, there are something like 900 years difference, but the central place is Plato. This is Plato, the philosopher, and Aristotle. They both encouraged mathematics, but in the picture we have a lot of mathematicians. Here is Pythagoras, uh, and we will stay on Pythagoras on his contributions, I mean, in mathematics and mathematics education. And here, one person you reckon, the important mathematician is Euclid, and he does geometry. It doesn't show very well in this picture because it's larger than life, this picture. So if you decrease it here, you lose a lot. And many other mathematicians, which I will show as we go along. The one who brought mathematics in school was Pythagoras. He lived around 500 BC. I have his dates over here. And for the ancients, he was a person considered as a sage, half god. So much important for them is that the following statement by Aristotle, I really love this statement. I mean, it's so false today, but anyway, they say that there are three types of logical creatures. One is gods, on one side, gods, the ancient gods. The other one is humans, man, and the third one is Pythagoras, who is in the middle alone. He's between gods and humans. So they deified him. He was a person for the Greeks, as was Buddha, Confucius for the Eastern cultures. And apart from his philosophy and way of life, he also did mathematics, original mathematics. For example, we have a statement when the so-called Pythagoreans were the first to touch upon this subject, that is mathematics, and improve it. And also we have many theorems of Pythagoras. Well known is the Pythagorean theorem. He's not the first one to discover. The Babylonians and Indians knew before him, but it seems he's the one who has done a absolutely correct proof from axioms. And I'm saying this because theorem of Pythagoras is equivalent to parallel axiom, and we don't find axioms in previous cultures. So the full proof, correct proof, is by Pythagoras of a theorem that was known at least empirically before them. The Pythagoreans discovered the 5 Platonic solids, which is a remarkable theorem. Here is all 5, but they prove that there is no other regular solids in space. And this is just these two are just a minor contribution, minor description of the mathematics of the Pythagoreans. And let me mention, because I want to discuss a little further on another topic. The story says that when he discovered the theorem, the so-called theorem of Pythagoras, he sacrificed an ox, 100 ox. The Greeks, when they felt that the gods favored them or they were asking for a favor, they made sacrifices. Usually it was a small animal. 100 ox is the ultimate sacrifice. That means he realized the strength and the beauty of that theorem. And the beauty comes in Greek mathematics quite often. They do discuss beautiful mathematics. So he felt such a present from gods to him, so he sacrificed the 100 gods, the 100 ox. The sources tell us that Pythagoras studied this topic, mathematics, and brought it into a free type of education. What is meant is up to that time, when you learn something, you had in mind a practical application. You might become a sculptor, you might become a shoemaker. It was something practical. But he realized that mathematics should be taught for the benefit of mathematics, not having the material world in mind. And this is how mathematics remained. It is, most of mathematics is abstract for the benefit of mathematics. And the sources, Proclus, an author that wrote commentary on geometry, says he investigated theorems mentally and abstractly. He went away from the practical geometry that the Greeks inherited from previous civilizations. Now, even the name mathematics, it was given by the Pythagoreans. Here is the text, I have it in translation. The name mathematics was specifically given to geometry and arithmetic by the Pythagoreans. It tells us two things: who gave us the name, and he called geometry and arithmetic, which was the mathematics they knew at that time, they called them mathematics. Why? What does mathematics mean? Mathematics comes from the verb matheno, which means to learn. So mathematics really means a learning, a topic, a subject for discussion. Because in his school, which we said he brought mathematics as a free type of education, mathematics was the main subject. So mathematics means the topic, the knowledge. And from then it remained as a main topic in knowledge. But why did he insist to have mathematics as part of his education? It comes from many sources. Many ancient authors tell us why mathematics was so central in Greek education, and we will see some. After that, mathematics, after Pythagoras elevated so much, we also had great mathematicians. Here is a picture of Euclid. These are modern pictures, and one by Archimedes. Outstanding mathematics, and the mathematics they did has not changed. I mean, we keep on doing it the same way. Of course, a lot of mathematics was invented after that, but most of the school mathematics we do, or the geometry we do, is 90% written in ancient Greek sources, and that survive. We know about them. And there's a lot more mathematics, like Archimedes. He did very hard mathematics, very high quality mathematics, which survives. We know of his mathematics. Now, the real reason we are doing mathematics comes from a statement by Plato. Many statements, but I like this one particularly. He says there are three aspects to learning: memory, sharpness, acuteness. Is a little difficult to translate what sharpness and acuteness means from the Greek word. Is very specific words, but he explains. So it doesn't matter the exact translation into English, but I think sharpness and acuteness touches the Greek flavor. He says, memory is retention of what you learned. Of course, when we learn something, you have to have memory, you have to remember it. Okay, there's no education if you can't remember a few things. Sharpness is the ease of absorbing knowledge. So when you study something, it has to sink in your head. It is clear that you must learn how to absorb new knowledge. But acuteness, which I painted with red ink, is the important thing that Plato says. Let's read what he says, translated. Acuteness is the ability to investigate matters that you have not learned. And what he means, because he explains after that, we are not going to learn everything, but you will have enough knowledge to be able to create new knowledge from this. And you ask questions and answer questions. So you discover things. And this is why we learn mathematics. It helps us, it makes our mind, gives us the ability to create new knowledge. I mean, the thinking process, it creates new knowledge from what you learned. And what an educated man should do is definitely he should ask questions, he should answer questions, or when he sees a situation, try to see how he can do it. In maths, how do we do that? We do a microcosm, a little bit of that. But how and when? When we do mathematics, we work with problems. We are given a problem. That means you're given some data, some conditions, and you have to invent what comes to find the solution. It is a road to invention. So it trains your mind to invent things with rules. And the Greeks had a notion that everything you say must be supported by a logical argument. You have to convince the others that what you are saying is true. Beginning of science, no arbitrary knowledge coming just like this, which is common with most people. And after they put mathematics as central in their school system, Plato himself, he had at the entrance of his academy means for ancient Greeks, education you get after 20, and usually they studied for more than 10 years. The university, let's say, your education lasted 10 years. You went in so much depth that it took 10 years to learn. And at the entrance of his school, of his academy, he had the statement. I write it in Greek there for you to see, but the translation is, let no one untrained in geometry enter the school. So if you don't know geometry, don't come in. What he meant is it comes from another anecdote of ancient Greek. After he died, in fact, the new manager, who was a student of his in the past, has the following story, that a student came to register at the school to study, let's say, university level studies. And this teacher, this manager, Xenocrates, asked him one question. He says, do you know maths? The student said, no. He says, well, I'm not interested. He sent him off out of the school. He says, if you don't know maths, you don't have where to hold yourself to understand philosophy, to make deductions. Mathematics will teach you deduction, so no mathematics, you know nothing out of here. So only if you knew mathematics, you have understood what logical deduction is, you were admitted at the school to learn higher philosophy. Now, although mathematics is so important and everybody agrees we should teach it, if you ask students why they don't like mathematics, I mean, some students who don't like mathematics, if you ask them, why don't you like mathematics? The studies show they give these one or more of these following reasons. They say it's the teacher's fault. The teacher is not good, he cannot teach, etc. They transfer the problem to somebody else. Also, they say that they are not bright enough, they are not clever to learn mathematics, they diminish their capabilities, they feel inferior. I mean, we get so angry when we hear this from our students, but anyway, this is what they say. Then it's too abstract and too many symbols. True, mathematics is abstract and it has symbols. We use symbols like exponents, subscripts, etc., pluses, minuses, because they help us. Now, you have to go through all that before you understand that these symbols are useful for you, but the student finds it too abstract, especially if he is a novice. And then they find mathematics as not useful. They say, I will not need it. In fact, the mathematics we need in everyday life is just minimal. You just should know how to calculate, little calculations with integers and fractions, little areas of some pieces of land. So if you buy a land or buy an apartment, you understand what area means and so on. This is it. So why are we doing so much mathematics? And the student says, I'm not going to need it, because they have not understood that we don't do mathematics for the usefulness, but for the quality and the thinking process. And we have to address this problem. We have to know what our students think about mathematics, and we drive them out. And we have a difficult job. I compare a teacher in class who has a variety of students from very weak to very good. Is like a maestro, a conductor in an orchestra. In an orchestra, the conductor has violins on one side, drums on the other side, but he combines all of them to have harmony. He is a master of all of them, and all of them give a good outcome. A teacher has to have a good outcome with his students. And in any case, he has to be enlightened himself. In fact, I'd like to say sometimes that I can forgive a child who's afraid of the dark. Like here, the child is afraid of mathematics. So if a child is afraid of the dark, I can forgive. What I don't forgive is a teacher or a grown-up who refuses to see the light. Okay, dark for the students, light for us. Now, the one of the things that Plato again says that how we should teach mathematics to overcome this problem of students that they don't like mathematics and they don't find it interesting. He says we should learn letters, that he means grammar and so on around language, and the numbers, he means in mathematics, things on mathematics, as they do in Egypt. Plato visited Egypt. They had a great civilization before the Greeks, and he discussed with the priests over there, and he visited schools of ancient Egypt. And he realized that when they learned mathematics, which is little in comparison to Greek mathematics later, but is impressive because it was very early, he said they were doing it by playing and with pleasure. And Plato insists that this is how we should learn mathematics, in a playful manner. You have to make it attractive. And I will give examples how we do in attractive mathematics. Of course, we also have to do some dull mathematics. I'm not saying we can do all the mathematics in a playful manner, because some things you have to learn by heart. For example, how to multiply numbers or how to add fractions. There's nothing fascinating about it, but you have to learn it. So some things that are dull for the student, I mean, we have to endure it. But as soon as the student learns a little more mathematics, we can do very interesting mathematics. Even at primary school, the high quality mathematics, secondary school and at university, you can get beautiful mathematics of great intelligent arguments and so on. But even in lower mathematics, where the student has very limited knowledge, you can do very nice arguments that the student will say, yes, I enjoyed it, yes, I liked it. And I will give examples as we go along. Anyway, to increase interest in mathematics, I have a list of things that we should do. The best and highest is pretty proofs and clever arguments. If you don't say in your career as a student, as you learn mathematics, that, oh, this was clever, this was nice, this was interesting, then you have not understood mathematics. Mathematics is full of such ideas, and we have to give students pretty proofs. Examples will come. Of course, what does pretty mean? We cannot define. Everybody recognizes what is beauty, but we cannot define it. But I think many arguments in mathematics, nice little theorems, nice little steps and so on, pass this test very easily. It's the number one for me. Also, applications to daily life and applications to other sciences. Many people want to learn mathematics because they will study some other science, physics, engineering, biology, and so on. So you can attract the students for their interests over there. They will need it anyhow. And applications in life, it is something that we should always keep in mind, although the ancient Greeks said we don't care about applications of mathematics, it is mathematics per se, but I think we have to improve that. Modern times say no, applications are important. Use of history of mathematics. There are wonderful anecdotes about mathematicians or their life or something. I said a little story about Aristippus before, but many stories that enhance the interest in mathematics. A very common one is Gauss, a story that he could add the numbers from 1 to 100 with a little trick when he was young, very young. So little stories like this embellish our teaching all the time. And as you go along, when you do mathematics, it's good to have its history behind it, not just of mathematicians or little incidents of life of people, but things that are central in mathematics, they have to come with their story. For example, theorem of Pythagoras has a long story from Babylonians to Greeks to the Arabs. And conic sections, geometric axioms, and so on, is always nice to hear the story of your topic as you go along. Extracurricular activities like math clubs, conferences, exhibitions also enhance mathematics. Um, you there are conferences nowadays that students participate. Several conferences, at least I know in Europe and in Asia, that they have conferences that the speakers are students. And everyone that I attended, I was quite impressed with the students. Of course, behind every student, there's a teacher. The teacher was there to help give bibliography and so on. But I saw students really excited, and also many schools, many localities have math clubs. They invite speakers to talk to the students, and so it's always a good thing to have around. It improves mathematics, makes people more interested. Another way to do mathematics, games and puzzles, they're of paramount importance. Although they are not in the syllabus, always it attracts students to thinking. And I will give example for mathematics of primary school that will do games and puzzles that attract them. They find very interesting. And also competitions with caution. Mathematics is not a race. A competition is a race, especially the hard competitions like International Math Olympiad and so on. The problems are extremely hard. Most students or most mathematicians cannot solve any of the IMO problems. Uh, so competitions is good for people who do like to work under pressure. Real life mathematics is not like this. Mathematics you do at home with pencil and paper at your pace. But for some people, it is interesting. And this is where this is what I like from Kangaroo competition, is not the hard competition that is for really gifted students. It is the mathematics that attracts you because of its beauty. Of course, we have in math in Kangaroo some very easy problems because the student we cannot crush him. He comes to a competition, he has to answer some of the questions. So he's got easy problems, but they go harder and harder. The last ones are quite challenging, but they are new. The good thing about the Kangaroo competition, I believe, is not sitting the competition, but the material you'll get out of it when you prepare for the next competition, the discussions you will have with your teachers and students, because you will find problems that they're out of the box, attractive problems. In every Kangaroo competition, there are several attractive problems that is good to discuss uh, with each other or with teachers. And on the opposite side, what should we avoid? Dry, routine, boring arguments. kills even the good students. You, of course, sometimes we have to give some routine things, but if we can avoid, because it puts students, let's say, to sleep. In fact, I remember there is a nice saying of the musician Verdi, great musician, and also he was saying that you when you go to a theater, everybody can forgive everything in a play. Whatever happens in the play is interesting, except for one thing, if it's boring. And I say, for us teachers too, if you're a boring teacher, they will not forgive you. Avoid excessive symbols. And also, when we teach math, sometimes teachers have the concept that they hide their thinking. They give you magically some step and so on without explaining how he thought of it. But our teaching is not the theorem, is the method to do it. So we should not hide our steps. We should explain to the student how we thought, because he will imitate. Every student learns. We all did. We learned a number of things, and then you apply them. It's a long process. Okay. And us teachers, we should constantly increase students' interest and enhance abilities. Let me elaborate a little bit about hiding our paths. I will come in a minute. So to summarize why we're doing math, because it is useful in life and practices, is helpful to other sciences, it is entertaining in the mind, to the mind. You must see mathematics as entertainment, and we have to teach mathematics that will entertain you. If you don't do that, you lose your student. And the most important of all is improve deductive powers. Okay, you have to support everything, as Plato kept on saying. Let me say some rules about some ideas about mathematics. We should keep in mind, I write 3 or 4 things here. We should keep in mind these criteria for mathematics, these objectives of mathematics, and we adjust our teaching. Otherwise, our teaching will go wrong. Mathematics is not a set of rules. Unfortunately, much of school mathematics is they give you the rules and no more than that. It is not a set of rules. It is a study of the structure of these rules. You have to understand why they work and why we are discussing them, not just formula like this. And many teachers give mnemonics for formula and so on, and that's where they stay. We don't want the mnemonic of the formula. It's good, it will help you sometimes, but you have to understand why the formula is whatever it is. Now, math is not just applications. In fact, much to the opposite, in my opinion, and looking at history of maths and my own research and my friends and etc., the main reason for advancement of mathematics is curiosity. I will give good examples about this. Of course, much mathematics goes ahead because science asked us for to solve a problem. Engineers want to know something about materials. Designers of aeroplanes want to know the optimum shape and so on. Of course, mathematics applications are important, but most mathematics doesn't care about applications. It is curiosity within mathematics. Usually a problem set by a mathematician, solved later, and then you do the next step. You ask what goes further on. I will come back to this. Teachers should not deliver only facts, but they should develop students' ability to discover new knowledge, the acuity that Plato said, always in our mind when we teach mathematics. And much of mathematics goes using problem solving, because you give them the data and you ask the conclusions, and that is why I want to discuss a little bit what does the word problem mean. Remember, I gave a list of words in English that are of Greek origin. I said mathematics was one, so we know it comes from the verb I learn. What does problem mean? It comes from the equivalent Greek word, problema, is the same word, and it means to put forth. And if you see the etymology, what exactly does it mean? It's two words, pro and balin. Pro means before, and balin means to throw something at you. It is as if I throw a question to your face. That was problem means. Really, it has changed now what it means. Problem is something very specific, but original meaning, and that is how it is used extensively in Greek mathematics, is a question thrown to everybody and they have to fight for it. And Plato says in one of his studies that the study of this discipline of mathematics, he discusses mathematics over there, should proceed via problem solving. You This is how you learn mathematics. In fact, I compare it by solving problems, you learn more and more. You need the use of problems to learn more mathematics. I compare it like you understand the value of water when you feel thirsty. Same with mathematics. You'll understand the value of problems when you need the urge to create mathematics. It has many advantages. When solving a good problem is a journey through creativity, you create new things, is imagination. Mathematics is more imagination than anything else, curiosity, experience, and perseverance. Usually a good problem, you can't solve it in a few minutes. It takes a long time to solve. And we have to learn to gain this ability. We sit down and work it, usually by trial and error. In fact, it's mostly error, but you have to be consistent and persistent when you create problems. It helps you in many ways. Like Pythagoras says, it's a free type of education. You learn many other things, not just the whatever is useful for applications. And a good theorem and a good proof brings together seemingly independent ideas. If you have a difficult problem, or if you read a good theorem, it brings things that appear unrelated, and somehow they weave them together. I like to compare it with poetry. A good poem, if you read a line in a poem, you cannot predict the next line. In mathematics too, in a good proof, what comes next is always a good surprise. And you have to gain this ability as you're doing mathematics. Now, about teaching, I said teaching discovery. It's important to learn how to discover things. In fact, the ancient Greek books of mathematics do the opposite. They don't tell you how they thought the theorem is ready, polished. Descartes criticized Greek mathematics, saying that they hide their path to discovery, is like Greek sculpture, that they only show the end product. I have here a statue of Venus, is probably one of the most recognizable ancient Greek statues. It was found 2 centuries ago. Unfortunately, they fought, and the ones who stole it, so her hands broke. She was found with hands, but they broke. This is the statue of Venus de Milo, is in the Louvre today, or Aphrodite of Melos. Melos is an island in Greece, that's where it was found. Aphrodite and Venus is the same name. Venus is the Latin name of Aphrodite, goddess of love. In fact, you see this in words like aphrodisiac. It comes from her name, goddess of love. So the one who made this statue, outstanding sculptor used to say, when I do a statue, I take a piece of rock, and the question is what to subtract to get a beautiful result. And this is when we do mathematics too. You find many paths, wrong path here, wrong path there. Then you clear the road, you pave the way for a nice theorem. Gauss also criticized Greek mathematics. He said they are like foxes when they are walking in the forest. They are hiding their trails with a tail, right? Ready product. In our teaching, no, we should not do ready products. You have to tell the student why a particular step, because you want to enhance his thinking. I mentioned before that mathematics is curiosity and not applications. Very good example are the conic sections. The conic sections come in from antiquity. They were discovered about 350 BC. And we have an outstanding book by Apollonius, the conic sections, called Conic Sections. It was the highest geometry of its time. It's a difficult topic. The Greeks did conic sections not as we do today with analytic geometry. They did it geometrically. It was the highest, most important geometry. And they're defined in a three-dimensional manner, etc. This is the ellipse, a cone cut by a plane, and so on. No applications in mind. In fact, it took more than 1,500 years, perhaps 1,700 years before applications come into mind. When Kepler, I have the next slide, when Kepler discovered that the planets move in elliptical orbits, then the scientists had the ready material from the conic sections of antiquity. So far, no applications of conic sections. They were just mathematics for the sake of mathematics. They were doing it because of curiosity. Now, to produce new knowledge, there are some factors that help you, or some nowadays that are in fact necessary. First, you have to study the literature. You need good teachers, right? Whatever you should know in a topic should be there. Secondly, you must be at an academic institution or research institution, correspond and interact with other people. Knowledge is not something we do, new knowledge today is not something we do at home, isolated. Usually you have to be in a group. Third, you have to study the literature very well. And sooner or later, you must have a bright idea, something new. And all this is what will happen to you if you keep on doing it. I'm saying this as a joke, of course. Now, and I also like when I say you have to read the others and work with others. Here's a very nice statement by Newton, first-rate scientist, British scientist, Isaac Newton. He says, "If I have seen further, it is because he was standing on the shoulders of giants." And the giants he meant were, he read Archimedes, Euclid, and so on. This is why he can see further away. You don't discover everything on your own. You continue what you discuss, what you've learned, and you go further. And the brightness, the idea, famous example is Archimedes, the famous story that he had a problem to find if the crown of the king he was serving was all gold or mixed without spoiling. And he thought the law of buoyancy. He realized how to find out without spoiling. And it was an inspiration. And the story says that he came out of his bath. He came out naked, in fact, and he was running in the street shouting, "Eureka, I found it, I found it." Okay. Now, I write here a few of my ideas of knowledge. I said about mathematics, but let's see a little bit more general knowledge, because mathematics is, as we said, from the word I learn. It is producing knowledge. The aim of education is not quick pursuit of information. It is knowledge. You have to go into depth of things. Wisdom is a combination of knowledge, experience, and judgment. As you grow older, as you learn more, you develop all these skills, and that's how you'll become wiser in life. Imagination is just as important as knowledge, if not more. Mathematics, you must use imagination. In fact, they say as an anecdote that mathematics is, listen to the numbers, 40% theory, 40% applications, and 40% imagination. I love it. It makes 120. Okay, but imagination is so important in mathematics and in knowledge generally. Unfortunately, much of our teaching is teaching to the test. We teach our students to enter university or pass a test and so on. No, we should be deeper than that, as Pythagoras said. And as we teach, we should develop skills to solve practical and theoretical problems and also ask questions and answer questions. They say a good scientist answers questions, a better scientist asks questions. He knows so much that he can ask more material, more things. He knows what is important. So, coming to the part that I want to show mathematics, interesting arguments and so on, that I draw them from recreational mathematics. There's a long history of recreational mathematics. The oldest I found is Rhind mathematical papyrus, ancient Egyptian of 1650 BC. It has a problem. I don't read it now for economy, but it is a problem of recreational mathematics. It amounts to find the sum of a geometric series, and he does it two ways. One is the hard way, finding all the numbers and adding them, and then a simple, clever proof, exactly the same as we find the geometric progression sum. A little trick, which is very interesting. So it creates your imagination. Great book is Liber Abaci, 13th century, early 13th century of Fibonacci, famous story, famous Fibonacci numbers and so on. They all come from this manuscript. It was before printing, of course. Okay. He has a problem about chess and grains. Again, it is geometric progression, and he solves it exactly the way Rhind Papyrus did. Okay, and these are the Fibonacci numbers, problem of rabbits. They are well known, so I skip them coming to interesting mathematics. So one thing that never fails to attract student interest is mathematical magic tricks. We gain two things with the mathematical magic tricks. First, what you do a trick to him is based on mathematics. To usually you guess a number. That's why the cold magicians call them telepathy magic. That means you pretend you can read somebody's mind. You don't. You do mathematics. And the benefit is that if you do a trick to a student, he wants to know why it works. Usually with theorems, if you tell them a nice theorem, most students are not interested, they don't want to know why. But a magic trick, they want to know why. And if you tell them how it works, then they go back they go to their friends and they keep on doing the trick to them, and they want to explain to them the trick. So you benefit that they discuss mathematics. Here is one nice trick for this one. This one you can do to 10-year-old kids. They will understand. You have these numbers in front of you. This is how it goes. I'll go quickly, but with students I do slower. You ask a student to think of any two-digit number, right? Secret from you. And so please, all of you, please think of a two-digit number, right? And once you have a number, you add the two figures. For example, if you had 23, add the two digits. If you have 23, add 2 and 3, makes 5. So you have two numbers, 23 and 5, just two of them. Okay, you've done, everybody, with your own numbers? Now subtract the two. In my example, it was 23 and 5. You subtract, you get a new number. So me now, I'm completely lost. If everybody does, I have no idea what numbers in everybody's mind, right? In fact, they have different numbers. Then I ask my whole class, the the number you found, the third one, look at it on the board. Okay, and I pretend I'm doing magic, and I tell him, oh, if you look at it on this board, is the number, have you done it? Please have a look at the number. If you do correct, then I ask them, is it in a blue circle and inside is a red circle and the numbers written with white font, white color? They all say yes, right? So I tell them, I tell my students, either I made magic to you so you thought the same number, or telepathy, etc., or there was mathematics. Of course, they realize that it is mathematics behind it, and then I come to the explanation. And how I do the explanation is the following way. For a mathematician, it's easy, the explanation, but you can do more tricks with this, is the following. I ask them, okay, you don't know the explanation, let's discover. I said, look at these numbers. Do you see a pattern? If you see something and you want to explain it in science, the first thing is you observe it. Do you see something strange? Do you see something that attracts your attention? And so on. If you see something, you're on the road to discover the secret behind it. It never failed that students say, yes, I observe that the multiples of 9 are all in blue circle with red circle inside and white number, all of them. Look at 9, 18, 27. I've drawn them. I have drawn this. They're all the same. And once they discover at least that then their number was like this blue, red, etc., and it is a multiple of 9, I say, well, can you explain it's a multiple of 9? And good students will say, yes, the number we had it was a two-digit number, so it was 10a plus b. Then we subtracted the sums of the digits, so we subtracted a and b. Okay, so it is 10a plus b minus a minus b. This makes 9a. So whatever you do, the answer is 9 times a number. So it is a multiple of 9. So I did not guess anything. I just knew you will end up with a multiple of 9. So I tell you, look at the number over there, and I've drawn all the multiples of 9 the same way. So here you are. I pretended I read your mind. Okay, it's a nice mathematical magic trick, and you do a little proof, but he understands what is a proof. Here's an argument. You prove that it's a multiple of 9. Here's a nice trick. You have this one in front of you. If you like, please use your pencil and the figure you have, and we play a little bit because I want to show you what comes out of it and then explain how it works, because this is more elaborate. What you do is on these numbers, you encircle any one of them. Here is, in my example, on the left, I circled number 7. You just circle any number you like, and then delete all the numbers which are above it and left or right of it, right? They're out of the game. Just the circled number. And you repeat this with clean numbers. You circle any other number you like, and delete whatever is above, below, left, or right. And you do that until all the numbers are finished. When you are finished, you'll have something like this. Okay, and I stress to the students that each one of you has a different set of numbers, right? There will be 4 encircled, but they're different. Okay, and then I start my magic. I pretend I read their mind, and I tell them, now let me think. Have you done it? I'm asking you now. Have you done it? If you add, I'll wait for 30 seconds, and I do that. Or here is an example, if you like, right? If you do it and you add the numbers, you will magically get whatever you do, you will get 39. Okay, so the students are impressed because they all get the same answer. Then I tell them, well, if you lose my piece of paper and you want to make with your own numbers, how are you going to do it? Now I'm doing a shortcut. With students, I take much longer because I give them actually 3 methods to construct it, but I'll explain one. One method to construct such a magic square and it gives the same answer all the time. In fact, I can choose what answer I like. In this example, it was 39. I can do anything. Is as follows. And it also explains why it works, right? Not only I construct it, but explains why it works. You start with a blank 4 by 4 or 5 by 5, any, but 4 by 4 is just right. 3 by 3 is too small, 5 by 5 is too big. And you put any random numbers on the edge. Here I have 7, 6, 9, etc., and horizontally. Just any numbers you like. And then I complete these numbers as an addition table. For example, here where the 9 is and the 1, I write on the row and column that they meet their sum, 9 plus 1. Here it is on the right. I do this for all the numbers. And I claim this square has the property I mentioned. That means if you circle one number and delete up, down, left, right, and you keep on doing it, we'll all get the same answer. Why? Right? Here is why. If you circle, let's say, the 7, right, which you will add in the end, is equivalent to adding 6 and 1, because the 7 was created as a sum of these two. So this 7 is the 6 and the 1 selected in disguise, right? Now, then if you delete the row and column, you're not going to reach this number and this number again. The other circled number, let me look at here. If you circle another number, let's say the 11, is equivalent to 9 plus 2. This 9 is different from the 6 before, because the 6, we're not going to choose anything from this row and column. The new number 11 is in another column. That was the rule. Okay, so the 4 numbers you choose are effectively the same as, this one is the same as this plus this. The 8 is 5 plus 3. The 11 is 9 and the 2, etc. So these 4 numbers, their sum is the same as the sum of these 4 and these 4, because they were done in pairs. So everybody will get what the 4 circled numbers inside have sum the same as the numbers outside that you started, okay, by construction. So then I asked the student, now make your own square, and I want the sum. In mine was 39. You do one with 45, right? And they understand the magic behind it, understand the explanation, and they've learned something new, and they go and show it to their friends. So quickly, let me come to another topic from recreational mathematics. I'm talking quickly because it's late, I know, and you're tired. Here is a nice little problem that they will understand what it means to be impossible. This is genuine kangaroo question. I constructed that. You have the following. You tell them a story. There are elephants in this row, some big ones and some small elephants. And when they reach the crossroad, each elephant turns left or right, independent of the others. After they've crossed all of them, left or right, somebody took pictures of how it was after. Now, it turns out that one of these pictures is false, can never happen. Can you tell me which one is the false one? And can you prove to me that it is impossible that it will be the situation like this? For example, the first one is possible. The first one is if this first elephant turns left, it's this one, then the little one turns left also, then the next big one turns right, all the others turn right, all the other elephants, big ones turn right, small ones turn left, you'll get this situation. You can't get this one, and you can get the last one, but you cannot get this one. Can you prove it to me? Don't tell me I tried and I couldn't find it. It got stuck. No, I need a good, valid argument. And here is the nice argument. The student will understand it. It's a proof that brings you contradiction. You've done mathematics in a light way, but you made the principle. When you reach higher mathematics and you do genuine proofs by contradiction, he's familiar with the concept. Here is the reason why this one is impossible. It's the following. Notice here the last elephant is a small one. So as this elephant reaches here, it will turn left or right. You don't know where, left or right. But wherever it goes left or right, this small elephant will be the last one in this row. If it turned right, the last one, so there will be others in front of him. He's the last one. So one of these two rows must have a small elephant as last elephant because it is last here. So, but on this one, you have two big ones, right? So it can't be. You did not see a small elephant as last one in either of the two, in one of the two. So it just can't work. Okay, so proof by contradiction. Student will understand it, and they will have fascination if you explain. They might not solve, but this is not the point. When you explain, here it is. They will understand and they will see an argument, a valid argument. Let me come to some more impossibility proofs. For me to explain what does impossibility means I tell him impossible means you prove that something cannot be done. Careful, cannot be done is not the same I couldn't do it. Students don't understand the difference. In fact, they insist if they can't do it, then it cannot be done. For example, I ask them the following question. We have a balance like the old one with arms and weights of 4, 6, 7, etc. The numbers written here. And I set the following problem. Can you put some of these weights on one side, on one of the arms, and the rest on the other, and they balance? If you think you can do it, you have to tell me how you're going to distribute the numbers. You have to tell me number 4 goes there, number 6 goes there, etc. Or prove to me that it is impossible. I found out that I've been doing it to students many times at lectures, that a good number of students can answer with a valid argument that it cannot be done. The reason is that you notice here, they are all even numbers except 1. So this 1, if you could distribute, it would go on one side. So here we'll have an odd number and then even. The rest would be even. And the other side were all even. Well, one odd number and some even numbers, sum is odd. The other side is even, so they cannot balance. So this is proof that it cannot balance. Or alternatively, if there was a balance, the sum of all would be twice the number on one side. So the sum of all would be an even number. But here the sum of all is an odd number because the 7 spoils. Okay, so this is an impossibility proof. So here's some nice logical arguments that are very clever and they show impossibility. I start with an example which is possible, not impossible. Impossibility for them to understand. I tell them a story. I said, this is my lounge. It's 6 by 6, and I want to tile it, and the shop sells only such tiles. So I go and buy 18 such tiles. Can you help me lay them on the floor? Everything. Yes, it's quite easy. In fact, many ways. I ask the students do it. Okay, and here are 2 examples. Okay, one horizontal. In fact, if they do all horizontal, I say, I want more imaginative solution. They do mixed horizontal and vertical. But I do this because I want to tell them there's millions of ways that you can do it. Then I say, I forgot to tell you. My lounge is not as I mentioned. It has a column here and here. Okay, it's 34 squares. Can you tile it? Can you try and lay them on the floor, 17 of those to make 34? And I know it is impossible, but the students start trying. right? And I tell them, try, make. I know you will fail, but try. Okay, so they try. After they fail and so on, uh, many students say, it cannot be done because I couldn't do it. I explain, no, this is not the reason. There's a better reason than that. And here is a proof of the impossibility, a very clever argument um, to be understood by everybody. And the student will say, yes, I liked it. You do the following. You paint the floor with two colors, like a chess, let's say gray ones and green ones. And you observe the following, that if you put a tile, remember the tiles are 1 by 2, if you put a tile anywhere, it will cover one gray, one green. If you put it here, it will be like that. If it will be here, it will be like that. Any tile you put will cover one of each color. But if you count, you will notice that here there are 16 green ones, just count them, and 18 gray ones. So if you cover the 16 green ones, you would have covered also 16 gray ones, but you have 18 gray ones. So after you cover those 16 and 16, there will be 2 gray ones left over. Well, 2 gray left over with one tile cannot be done. So whatever you do, there will be 2 gray ones left or worse, but at least 2 gray ones. It is an impossible situation. Okay, and they will understand it. Of course, you have to do it taking your time. Another example, I say this is a museum, and the guard wants, his job is to pass from all the rooms, moving horizontally or vertically, not diagonally. And he wants to pass it from all the rooms exactly one time, he doesn't want to pass twice from each room. You have a paper in front of you. You can try. This is quite easy. This is to understand the problem. The real problem comes later. Okay, find the path from here to there, from start to finish. Many paths. I ask the student to draw some paths. Here are 2 examples. Again, I stress that there are millions. Then comes an interesting problem. Okay, I want you to start from here and finish there. Same rules, horizontally or vertically, through all the rooms, no room twice. Let me wait 30 seconds. Please try on your paper. It will fail, I tell you from now. It is an impossibility thing, but please try. The point is, why is it impossible? I wait a few seconds. Joanna will finish in a minute. So when you try, here is the argument that it is impossible. Again, you paint it with 2 colors. And how I do it to students, I say the following. Try and make a path, okay? It will fail, but try and make a path. What do you observe? Well, the thing to observe is that you will start from a red square. The next one will be gray because red only is neighbor to gray ones. Then it will be red, then gray, because every time you're in a red one, the next one will be gray because red is neighbor only to red ones, to gray ones, and gray is only neighbor to red ones. So this path must go red, gray, red, gray, red, gray, right? And I elaborate on that. So tell me, I ask the students, the red ones are which room? Huh? They say the first, third, fifth, and so on, at the odd numbers. And the gray ones are 2, 4, 6, etc. We talk a little bit about odd and even. And then I say, let me challenge you. Let me challenge you. Number 20, room number 20. What color is number 20? Uh, they will they will argue. The students understand and say, well, 20 is an even number, so it is gray. Good. Number 27. They say, oh, it's an odd number, so it's red. Then I make the trick questions. I said, tell me number 38. What do you think? I ask you, audience, what do you think about what color is number 38? Well, this is a joke. There's no 38. They're all 36. Okay, so after I make the joke, I say, yes, they are 36. And what color must number 36 be? They say 36 is even, it must be gray. Well, if it's gray, this one cannot be the last one. You cannot start from red and finish at the red. We said the red are 1, 3, 5, 7. So you cannot have number 36 as red. So this square at the top cannot be the last one. There is no such path. Before this one was the last one, was gray. That's fine. Okay, but going to that one is impossible. It is an impossibility proof with coloring. It's a delightful argument. It's by a mathematician, now he died, Golomb, American mathematician Golomb. And then in mathematics is versatile. If you use a technique, then it can be applied very often. It can be applied in similar situations and sometimes not so similar situations. Here is a similar problem, which I do. I want to see if they understood the technique. It has slight variations, so if they understood, I will be satisfied. They will not fall into the trap. I tell them this is another problem. This is a piece of cheese, which I cut in 3 by 3 by 3, 27 little pieces. There is a mouse which starts eating one piece, the bottom left one, and when it finishes this one, it passes in one of the neighbors, either up, horizontally or vertically, not diagonally, either up or forward or left, etc. And when it finishes that one, it goes to the next one and so on. But I have the following rule. I want the mouse to finish on this one, on the middle one, right? Somehow find the path horizontally, vertically, whatever, but I want this one to be the last one. And they've learned the technique. I say use the coloring, as I said, and here is coloring for you. Now I color them with two colors. And here is the same three. I open them a little bit so you can see inside. And I said, well, he starts with the red. I want him to finish at the green one. Here, the last one is opposite from the previous. They were even in here. If there was a path, again, as before, the red ones will be 1, 3, 5, 7, etc. And the last one has to be, since the 27 is an odd number, has to be red. So you cannot finish on the green one. Okay, this is an impossibility. I'm satisfied if the student gives me this argument after he heard the previous one. Okay, anyway, this is where I finish. I think I exceeded my time. Wow, 7:15, huh? Thank you for your patience. Joanna, I'm in your hands. Yeah.
Well, thank you so much, Michael. We have just a few minutes. If you have any questions for Michael, he could answer. And maybe we can start with whoever has something to comment or question for Michael. I think, Michael, people are kind of shocked with all the knowledge because you have it all. You have the knowledge, wisdom, and imagination. So
Yes,
you brought
a
so
lot of
much.
material. I went
Yes, a
through
lot of.
history.
There,
I went.
there's a question asked to explain the last question again.
Sorry, the last question.
Yeah,
This
they
one.
want explanation again.
For this one, or
Yeah,
you
for
want
this.
Okay.
Yeah.
Yes. Here, I ask to go from red, and after I color them. In the first stage, I don't show them the colors. I say I want from here to here. So effectively, I'm asking the first cube to be number 1, and the last one is 27. If you paint them, they see that the odd ones numbers are red. 1, 3, 5 are red because every red is neighbor to green ones. From red one you'll go to green. Green one are neighbors to red. So the path must go red, green, red, green, red, green. Okay, so the red ones are number 1, 3, 5, 7, etc. So the last one, the number 27, because at 27 now, must be red. Okay, but so you cannot finish on this one. This is green, so it can't be number 27. Okay, the others can, but not that one. So it is impossible. You cannot reach that one as last one. Okay, it's clear now?
Any more questions? You can unmute yourself. If you want to ask a question directly, you can unmute yourself.
I was just wondering what grade level is the last question? Thank you.
You can do for 10-year-olds. For smaller class, although they understand the argument, there we have the obstacle that they don't understand the difference between I cannot do it and it cannot be done. Okay, for many students, so they will destroy your lesson. But for 10-year-olds onwards, they will understand it, especially if you do 2 or 3 examples. Well, I did one with the museum going from room to room, and from here I test if they understood the principle. And it has a small difference. Before, the last one was even, but they were even. It was an even number, and it was same color. Here it's an odd number; it's opposite color. Okay, so it has a little. You'll understand if they understood the principle. And there's wonderful problems. This is just the tip of the iceberg. This technique, the coloring technique, you can show impossibility proofs or even possibility cases for cases that the problem can be done. Very wide. In maths, if you want to talk with higher maths, it's theory of invariance. It touches the theory of invariance. What the invariant means something doesn't change. Here, what doesn't change is the color of every second cube. It's a beautiful theory. I have millions of examples on many topics. Here is only a little bit. Joanna, if you ever want, without the theoretical, I talk too much about what is mathematics and so on because I want it complete. But if you want a session, just little problems like this, so people will have material for their class, I've got millions. Welcome anytime. If you wish, you just tell me and we can have a session.
Thank you so much, Michael.
Yes,
Without
thank
the
you so
theory.
much. I want to also tell everyone that if you like the history and mathematics that Michael showed us through the session, you can also read a lot of beautifully written articles that Michael authors in the newsletter. I'm going to send a link right now. In this newsletter, for the last 10 newsletters, Michael has a section, Scripta Manent, and he basically combines history and mathematics, why something happened, why certain words are called this way, and why mathematics was invented in this part of this maybe point of history. So very captivating stories. If you go to this new newsletter, there's a section for Michael and Michael's articles. So these would be fun to read as well.
Yeah. Yes, therefore, literary style. But it is phrases that are relevant to mathematics, but are used by intellectuals.
There is
Well, I mentioned that no one who knows geometry should enter of Plato. Phrases like this, relevant to mathematics.
Michael, there's another question. They ask, is there any PDF or book for this kind of questions?
I intend to write. Yes, I have wonderful material. Now that I stopped Kangaroo, I did a lot of work for Kangaroo, and it kept me behind things that I wanted to write. I produced problems and so on. It's time to collect them and write. I will send to you, and you can distribute to all Kangaroo. I'll be more than happy to do it. Yes, I have wonderful material.
Yeah, and I want to add that Michael also has a lot of material in Greek. So if you know Greek, you can have even more than English. But with nowadays with
Greek
AI,
is
I think everything can be quickly translated.
Yes, yes, but I will write in English, but I know the Greek is spoken by only a handful of people. If you think of China and Greece, is another scale altogether. Well, I know Greek is a difficult language. That in English, there is an expression. It sounds Greek to me, right? If it's something strange and high quality, it was they had this expression. So I know the difficulties of Greek um, for how people perceive. And now it's a dead language. I mean, ancient Greek is only spoken by locals here, and that's it. Okay, it was not at one time in history. It was like English today. It was the lingua franca, the language that all intellectuals spoke. Gone, and the Bible, for example, is written in Greek because of that, because it was the language. I mean, the stories of the Bible are not stories about Greek people, but it was written in Greek because of being the language of spoken by intellectuals.
Well, thank you so much. We have the recorded session. We recorded the session, so we will share with all of you the link to the session so you can maybe pass it on to people that couldn't participate or people that didn't know about the session. So you can share the link as well as the PDFs. Michael graciously allowed to share all the slides with you, and we'll share with everyone.
My pleasure. Yes.
Yes, thank you so much, Michael. It was an honor to host you here for our US international teachers, educators, friends, and everyone who likes history and mathematics.
Good. Yes, we can repeat. Yes.
Thank you so much.
Bye-bye. Yes. Thank you.
Good.
Yes.
Thank you so much.
Thank you.
Bye-bye.
Thank you, Michael. That was
Thank
amazing.
you.
Thank you
Thank
for
you.
thank you. And regards to all my friends there. I have plenty.
Thank
Thank
you.
you. Thank you, Michael. Just a
Thank you,
quick, do you
Michael.
have a quick tip for students to increase their resilience? Because they'll be like, oh, this is too hard. And they'll just walk away or something.
Well, I said at the beginning, remember, I said that the students said, this is not for me. I'm not clever enough. It is a difficult problem. We teachers must look after all our students. So it's good ones or bad ones. In fact, there's a nice story. The philosopher at the beginning, which I said that with the sunk ship, he has also the following story. He was a great philosopher, and somebody asked him, "Why do you teach weak students? A philosopher of your quality, why do you bother with little people who are so weak?" He says, for the same reason, like a doctor goes to treat the sick people, the healthy people don't need it. It is my duty. Okay, so I love this thing. And yes, we have to teach even the weak ones in mathematics to enjoy thinking. I mean, not just thinking, but enjoy it. And with little puzzles and so on, magic tricks, you can't go wrong. It will awaken something in his heart. So, yes, our duty, like the maestro in the orchestra.
And I
All
think
right.
that was
Thank you so much.
You're welcome, and thank you, Michael. I think that was the idea of Math Kangaroo, to be for everyone and also to have different difficulty levels. That's why we have 3-point questions, 4-point questions, and 5-point questions. So every student can find something for themselves and be
Yes.
Motivated or acknowledged that is able to do some of the competition questions. As we know,
Yes.
some competitions, the questions all are extremely difficult, or all are only for selected audience of students that are doing really well. Math Kangaroo is for every student, for everyone that
Yes.
that has all sorts of abilities. That's why we have different points and different levels of difficulties.
Yes, it's good material for class. I mean, maybe after class, clubs and so on, because they're just right. They're challenging enough, but not killing. They won't kill you. You will understand the solution even if you don't solve. And most people might not solve all the problems. It's no harm. Like Newton said, he was standing on others, on giants. He could see further. We learn so we can apply the acuity of Plato. So you learn how to discover new material. Yes, that's how life goes on.
Wonderful. Michael, I think people don't want to go. They want to keep going with asking questions or.
Yes.
It's okay with me. It's okay with me.
Hello.
Yeah, please stay. If you need to go, you can finish the session and leave.
Yes.
If you
No,
want to
I'm
stay,
fine.
Michael,
I
could
am
you
fine.
stay a few more minutes?
Yeah, I want
As
to ask.
long as you like. As long as you like.
Can I ask
Okay.
Michael one question?
Yes.
This is Simon Oyo.
Simon, I recognize you.
Thank you, Michael. You see, you have advanced a strong point that you gave an example of somebody who said, I stood on, that's Einstein?
Newton, yes.
Isaac Newton, yes.
Yes.
Said he stood on the shoulders of others.
Yes.
Now, this presentation is so great to me
Thank
that
you. Yes.
I'm asking you one question.
Yes.
Whom do you anticipate would be able to stand on your shoulder to see like
On
Isaac
mine?
Newton did? On your
No,
shoulder.
I'm too small. I'm too small. Too small. Too small.
Now, you are small in your eyes, but you who has presented very great thing to me.
I do really, Simon, I love to share my knowledge. Teacher in my blood. I enjoy creating little new mathematics and giving it away. I have wonderful material, really a lot of material. Somehow I have to write it down. And as I have started writing, but it is in Greek for this stage, history of mathematics. I have fantastic material, and that's serious mathematics. I'm doing Greek mathematics is difficult, but I record them after teaching it so many years. I realized that I must leave scripta manent. What is written remains. And I intend to do also with very nice problems. Well, Joanna said, I have produced more than about 800 questions for Kangaroo. They were not all chosen because they cannot all be chosen. In a competition, you have to have distribution of questions, 3.4 points, so many geometry, so many. It's not bad not to have problems selected. It's not. It's perfectly normal. But most of these 800 questions are very nice. Um, uh, Something like 30% of them were selected, which is a high number, but I have more also very nice problems that somehow they're lost. They are lost. I have to write them down and show them because they have also the right difficulty. Some puzzles or math problems can be very difficult, so they're frustrating. But if it's the right, it has something nice, something new, little clever step. This is exactly, I spend a lot of time to produce problems that have one little small clever step. That's enough for me. I don't need big steps. Yes, I think all the time. When I send problems to Kangaroo, I used to think all the year round. I jot my ideas, a piece of paper, and that's it. I send. In fact, Kangaroo has a regulation to send 60 questions. In the past, it was free, not a bound. And 60, I sent 60. Once I sent 120 or something like this. Yes, I love doing it. Yeah.
Yeah, that's very true. Michael wrote hundreds and hundreds of questions, and all there's a depth to the question, and there's a lot of ideas. And if you could share your ideas, Michael, where we can find the ideas to come up with questions. We all know mathematics, and where do you find the ideas? By looking at the world, by looking at your house or outside the nature or your classroom?
I tell you, there is no clear answer to that. I have my radars open all the time. I might see for example, one source is that you see a nice problem and you see the idea. I don't like to make a same problem or very similar. It doesn't count. But mathematics is so versatile. You can have one idea. Many times I see an idea and I have a problem which improves the idea, or it's a more interesting problem. This is one good source. My mind and my eyes are open 24 hours a day. Well, I tell you this much. I have a forum in Greece. Unfortunately, it's in Greek. It's a math forum, quite successful. I have written 18,000 answers. I mean, people propose problems. I also propose all the time. And I have 18,000 responses. So I'm all the time. I have problem books. I have puzzle books. Everything. I sniff them, so to speak. If I see something, it clicks something inside me, right? And cultivate it, or write it down and come back to it. Many times in my notes, I say, make a problem out of this, right? So I have let's say the trick, the technique, the idea, make a nice problem out of it. And I have on occasions, I'll show you problems that the idea is known, but the problem is dressed so differently and it make it an interesting problem. The presentation is nice. I think on the printout I gave you, I have three-figure numbers, and I say found the missing ones. All right. This could be with letters, A, B, C, the missing ones, but you have the paper one on top of the other, it hides something, so it is a little mystery. But as a problem, it's known. It's known, but the presentation is better. Okay, all the time I do that.
And Michael, who is your giant? Which giant, which shoulder, on which giant you're standing?
I'm without hesitation Archimedes. I know Archimedes very well. I've read, it is very difficult, and most of the books of Archimedes survive. He's lucky among the ancient Greeks because most of Greek mathematics is lost. But of Archimedes, we have most of his. Many are preserved by Arab mathematicians who translated into their language, and sometimes the Greek is lost, but we have the Arabic. So most of his work survives. Is brilliant and difficult and clever, and for me, he's my giant.
Okay.
And from modern mathematicians, Euler. Yeah. So versatile. Euler did all of mathematics, differential equations, graph theory, calculus, whatever you name it, he's there. Geometry, he's got wonderful. I've read most of his works. Now you can find them online, either in the original Latin, most of them are translated. I think it's called the Euler Project if you search for it. I've seen so many papers of Euler. I love him. Yeah.
Great. Any questions? Any other questions for Michael before we go?
I have a comment about what Michael said, that he stands on the shoulder of Archimedes, and that's at a standpoint. Maybe you can correct me, but I heard you mention Archimedes as a pillar.
Yes.
Yeah, and I think we may be having different perspectives, because when I was still a small child, and then when I reached high school, I found that what Archimedes discovered about the principle of flotation was something that I knew when I was still a young boy going to fetch water from the stream with a saucepan. Then, and I didn't know that there is something far much and so magnificent
Yes.
about this Archimedes. Well, now
Mm.
one thing I wanted to say here is that, like you were saying, everything I see around myself, whenever I walk or whatever I do, I look at mathematics.
Yes.
But
Yes.
when I try to frame some questions, quite often I get some solutions, and I find that some people are not able to understand. I am not able to convince some people with the solutions. Just like
Yes.
in your presentation here, I've been getting a lot of difficulties in understanding this, except, for example, this last example here.
Yes,
So,
I went too fast. Yes.
so, but yeah, well, that is true. Of course, now it is after, so it's coming to 2 a.m. in Uganda. So the head is a bit tired. I've been working the whole day. But this may be a lame excuse. But one thing I can try to say here is that it really takes a lot of time. It requires at times some consultation and concerted effort to be encouraged by somebody who has gone ahead of you, like Michael. Now, Michael, you are not very, you are a rare commodity. How would you
Thank
advise
you,
us
Simon.
to? Yes. How do you advise us to, to access you in some of these areas, because you have the experience you have, you have gone ahead of us, and it would be good wisdom to get an opportunity to stand on your shoulder if you can allow that happen.
Yes. Anytime, Simon, I promise. Uh, Now with Zoom it's easy, but really I lecture a lot. I get invitations also to many countries all the time I travel. But also Zoom, I've gone to schools, hundreds of schools, universities, math societies, and so on, and they enjoy my lectures. Of course, live lecture is better than yeah, Zoom, but I really do my best. And now that I've retired, I promise myself that it is my duty to record it. Before I just said, doesn't matter. But now I see that time is limited, and I have to live, I have something to leave behind me. And this is what life is the trail behind you that matters. Um, yeah, so I will do it. It's a promise, and I will send to all my friends.
Thank you very much.
Yeah.
Yes.
Thank you.
Thank you very much, Michael. We probably finished the session. Last chance. Any question for Michael?
Yeah, hello. Can you hear me?
Yes, please.
Okay, Meshach?
Yeah, Prof. Thank you very much for such a wonderful presentation.
Thank you. Yes.
Now, some people make the assertion. I want to take your view on some assertions people make that no matter what you do as a teacher, some students can never like mathematics, or there's no way they can come to appreciate the subject. They will never be able to learn anything. They are not born, or they are not made for the subject. What is your take on that assertion?
Yes, it's absolutely true what we are saying. All teachers all have this experience. That is why I feel that for such children, the aim is not to teach them mathematics. They won't like it and so on. But if you do little puzzles, little nice, clever arguments, that you will understand, this is sufficient. They've got other skills. I mean, mathematics is not the only skill in life. Some people have altogether. Most people don't get mathematics. You know, when I meet people, I say I'm a mathematician. I say, oh, you must be very clever. No, everybody has his own skills and characteristics. But for students, all I want to teach them is how to think and how to enjoy thinking. It's so important. It's for them. I mean, so important for them. The opportunity to enjoy thinking is wonderful. Some people might enjoy by playing a chess game, others by solving a crossword puzzle, others by saying jokes. Whatever it is a process that you must have, a process that you must go through. Yes. Yes, not everybody will like mathematics. You cannot teach everybody mathematics. But anyway, at least if they can think and give them ideas how to in their life when they meet a situation to give a solution to it, because life is full of surprises, things that not planned so well in life. So you have to make decisions every now and then. So you make a good, wise decision, right? So you give them the skill, and as teachers, it's our duty to do so. Yeah.
Thank you very much.
Yeah.
Can I step in a bit?
Sorry?
Can I step in a bit?
Yes, yes.
Yeah. A few years of my teaching mathematics for about 40 plus years, I really thought I didn't find students who complained about my teaching, and they always they always hailed me and thought I was, and either flattered me, they thought I was a very good teacher or one of the best teachers, including my wife, who confessed that if I was her teacher, she wouldn't have got F9 in a high school examinations. And I always felt flattered. But then I realized that I think one of the factors that made me to like the subject later on is the fact that I had a very difficult foundation right from childhood, where I developed a positive attitude towards trying to overcome every challenges that I had from childhood. So I think some of the factors that we need to do is to enter into the mind of these children and
Yes.
try to enter into their brain and try to develop them together with have all the empathy and try to bring them up,
Yes. Yes.
feeling to be part of them, and then they begin to appreciate that, oh, you are also inside him or inside her, and in that process, at times I use that type of approach, and I found that I was able to change the attitude of these children and align it to like mathematics, and many of them up to now continue to appreciate the little contribution I made in their life. Some of them have turned to be great scientists. Some of them are in different parts of the world, still sending me messages of what I thought I was just doing out of my own, feeling for them. But they later said that this was very great thing, and they are great because of what I contributed in their life, which I didn't know, and I didn't think I was doing anything.
It's such a fantastic feeling. I know, because I also get feedback sometimes from students who became uh, maybe mathematicians, maybe physicists, maybe lawyers, maybe whatever.
Yes.
They say, I learned something from you. For me, it's a great pleasure. It's a great pleasure. If you are inspiration to a student, is so nice. Yes.
Thank you.
Well, we have a difficult job and important job.
Yes.
Yeah.
Yeah, Michael, we have to do it again.
You're welcome. Next time, no
Yes.
theory, just examples. I've got nice math, no need to say what is mathematics and the word mathematics and the word problem and Plato and so on. Just straight little games. Nice material. I have nice material.
But it
Yes,
was
thank
beautiful introduction, seriously. It's just amazing.
Thank you. Yes.
Michael, we teaching mathematics or facilitating the competition. We are surrounded by math all the time. However, we're not surrounded by the history and where it came from. So this part was unique and additional to something that we kind of are embraced on everyday life.
Yes.
But the history touch was just a beautiful addition to everything that was said today.
So I believe very much that when we learn maths, we should learn its history. The same as doctors, they must learn the history of medicine, etc. And unfortunately, we don't learn even at university at a degree. Either they have most universities don't have a history of maths course, or they have a very shallow one. But in life, of course, you can buy books, there's the internet, you can elaborate, especially if you specialize on something. Greek, mathematics, Arabic, Chinese, whatever, you specialize on something, read the literature, you will get great satisfaction and it will satisfy your curiosity also. And you will learn lots of things and the interconnections. This is the beauty of mathematics. There are things that look apart, they're the same. There's the same heart. They have the same heart, and it's great enjoyment if you find out how concepts evolve, etc.
Well, thank you so much. We thank everyone for participating in the session. Big thank you to Michael. We'll show everything we have from Michael and probably more, because knowing Michael, I know you'll send me more material to share with teachers. So I
Yes.
expect even more what we shared today. So I'm very grateful for you,
Definitely.
Michael.
It's
From
a
the bottom of
promise.
my
It's a
heart, thank
promise.
you very much.
Okay.
And thank you,
Okay.
everyone.
There's one more question.
Yes.
Michael, if you could give a quick suggestion.
Yes.
A teacher asked they prepare for the grade 5 students to join the Math Olympic competition, and they ask where to start to train the students,
Oh.
grade 5 or even younger.
This is another level. The big competitions, not kangaroo style, IMO, is for really gifted students, and they need gifted teacher. The teacher must be very sophisticated because the problems are difficult, and the student will get disappointed if he doesn't find first-rate material. Fortunately, there are very good books. All the books of Andreescu are very nice, and some of the old Russian books are also, they are all translated into English or French and German and so on. They have nice material for Olympiads. You have to start from the beginning. Don't make the mistake and go to solving IMO problems because they're so difficult. You need a lot of experience. It will take you many years to learn, but it is possible. I mean, knowledge is cumulative, and there is good bibliography. There's the internet, but it is a lot of work. Because I was teaching students. I was for 2 years. I was the leader of the Greek team. I've done 2 IMOs and 2 Balkan Math Olympiads. Once a student, I was teaching a question. He said, "How many hours did it take you to solve the problem?" My answer was, "Don't ask me this question again this way. Next time you ask me how many nights it took me." Right? I don't solve a difficult problem in few hours. I just cannot. And if you are honest with yourself, it will take you days, nights, weeks, doesn't matter. This is the perseverance. And that is why we are doing it. I know many teachers say, "Oh, easy problem." You must be joking. There are no easy problems. They're not easy. And I'm honest with my students. I say, "Yes, it took me nights." Yes, correct. Yeah. So if you go into this field, you have to spend nights. Yes. Nothing free in this world.
Thank you, Michael.
Yeah.
Okay, Michael, it's exactly 1. Is it 1 a.m. in Greece now?
Yeah.
I suppose in Uganda also it's 1 a.m., right?
No, it is 2 a.m.
2 a.m. Wow.
Yes.
Yes.
It's time to go to sleep, right?
Yes,
Ah,
please.
well,
Yes.
I have to drive home. I have to drive home.
Oh,
No,
I'll see
20
you here
minutes.
in
It's
your
not far.
office,
It's
Mike.
not far. It's not far. No, yes.
Yes.
Okay,
Okay.
well, thank you so much. And we hope to see you again, Michael.
Yes, my pleasure. Anytime. Yes.
Thank you, everyone.
Thank you. Thank you.
Bye-bye then. Yeah.
thank you. Thank you, Michael. Thank you, everyone. Yeah.
Thank you.
A wonderful
Thank you.
weekend.
Thank you.
Same to you.
Bye-bye.
Bye-bye.
Bye, everyone.
Bye.